Greetings and welcome to lecture number 7 on internal flow. That is, this session we are going to discuss the siphon principles. Actually, we come across many applications where the water is transferred from one reservoir to another reservoir, separated by a hill or high level elevation, or it may be the water is transferred from one side, the other side of the dam. If the gates are closed, generally, this pipe, the hose flexible pipes are used to transfer the water from other side of the dam to this side. Or this is the case where the water is transferred from this a small well from this farm. These are the piping laid down, or these are the piping arrangement for of the hilly area. So this is the pipeline where the water is transferred from the channel to the other side, because channel doesn't have any kind of outlet. So instead of using the pump, we can use this natural principle, that is siphon. Or in practice, sometimes we use this technique from drawing petrol from the tank to the small tank or small can. So these are some practical applications. This all this piping arrangement is called a siphon. So in order to transfer this water or any liquid from one level to another level separated by a hill or a high level elevation, some principles are used, and how to analyze this kind of principles, or how to analyze this kind of pipings, that we are going to discuss in this particular session. So siphon is a long bent pipe used to carrying water from reservoir at high level to another reservoir at a low level, separated by hill or high level ground. It may be a ground or hill. So such arrangement, that is called as a siphon. The point C is highest point of the siphon is called as summit. The pressure at C is less than the atmosphere, as it lies above the free water surface in the tank. Because this level is above level A, suppose up to this particular level the pressure is atmospheric, and beyond that the pressure is below atmospheric, you can say this level here. So pressure is lowest here. So after that, it continuously pressure decreases. The pressure is lowest here. The portion between reservoir A and reservoir up to C, that is called as an inlet leg. This portion is called as inlet leg. And the portion between summit and reservoir B, that is called as outlet leg. That is shown here. This length is always, most of the cases, this length is shorter than the length of the outlet. So this is the general orientation of the siphon. So maybe this orientation changes. Now we have to make sure that flow must be possible, because here there is some elevation, and if this height is slightly exceeds, then the flow is not possible. So the pressure at C can be reduced up to absolute zero pressure, because fluid always flow from high pressure to low pressure. So, but practically this pressure is should not be 10 minus 10.3, because 10.3 means absolute zero pressure, 10.3 meter of water minus. But in actual practice, it is only minus 7.6 meter of water, or we can say 2.7 meter of water absolute. So this is absolute pressure, we can say. If the pressure falls, becomes less than 2.7 meter of water absolute here, the dissolved air and other gases would come out from the water and get collected at the summit, and it may be obstructed. It may obstruct the flow of water. That is the case. So we have to make sure that as this pressure increases with increasing height, suppose, and sometimes if the dissolved air or other gases, if it come out from the water, it get collected here and the flow is obstructed. So we have to make sure that pressure should not fall below 2.7 meter of water. The condition. As far as working of this siphon is concerned, the negative or vacuum pressure is created here, and so that the liquid gets pushed into it, because fluid always flow from high pressure to low pressure. So because of this negative pressure, the high pressure to low pressure, and here due to gravity it falls down. And then in order to push, in order to get the water here, so this pressure difference is responsible, and then the gravity force is responsible. Like that. The velocity or discharge. Now, in order to analyze this particular siphon, we have to apply the Bernoulli's equation, because this is again an application of Bernoulli's equation. So generally, we can apply the Bernoulli's equation in order to analyze the siphon piping. Analysis of siphon piping means for calculation of the length of the siphon, the geometric parameter, length or diameter, or what should be the length of this inlet leg, what should be this elevation, means that is the pressure should be there. Then what is the discharge to the piping, what should be the diameter. So all these parameters we can analyze. So designing of siphon, we can say, or if the existing pipes are there, then how much discharge we can draw with the help of that piping. So such kind of analysis we can do by applying Bernoulli's equation. And only in these things we have to apply the Bernoulli's equation twice. First of all, we have to apply the Bernoulli's equation between A and B, and then we have to apply the Bernoulli's equation between A and C. So only by application of this Bernoulli's equation, depending upon the information given in the numerical information available. So either which one we have to use first, that is Bernoulli's equation A to B or A to C. That depends on the information available. But most of the cases, Bernoulli's equation between A and B is always found convenient, because most of the parameter at A and B, they are zero, except elevation part. Otherwise, pressure velocities are zero at both points. So from the given information, almost 90% cases, there is a possibility of application of Bernoulli's equation if the diameter and length are given, in fact. Then we can apply the Bernoulli's equation in order to calculate the velocity. This is about the analysis part of Siphon. Siphon is used, as we have discussed in the previous slide. It may be used to take out water from one reservoir to another reservoir, separated by hill or high level, or reach, we can say, or high level ground. To drain out water from the channel, that also we have seen, without any outlet. Then to take out the water from the tank, which doesn't have any outlet. So that also we have seen that the petrol is taking out from the tank to the can. So these are some common examples of siphon, but it is essentially a long bent pipe, and it may consist of three parts, that is inlet leg, outlet leg, and summit. So these are the three important parts of the siphon. That's it. This is all about the siphon. Now we'll discuss how these siphon principles are used to analyze this piping with the help of this example. Suppose in this example, the two reservoirs having a difference in elevation is given, that is 15 meter, then are connected by 200 diameter siphon. So diameter of the siphon is 200 The length of the siphon is 400 which is given. Summit is 3 meter above the water level in the upper reservoir, and the length of the pipe from upper reservoir to the summit is 120 meter. This length is 120. Coefficient of friction is given, but this is 0.05. So we have to consider this is f dash value. So these values are given. We can write these values in appropriate notation. Diameter d, length is given, difference in elevation, that is capital H, then height of the summit from the upper reservoir, that is this small h is given. Coefficient of friction that we calculate, that is friction factor, that's Ricebus coefficient, by multiply this by 4. So generally we have discussed that if this value is point not something, it is always f dash, this coefficient of friction, not friction factor. But if we are using FLV square by twice GD, we require F is in that case is a friction factor. Now, as from the given information we have, if we know the diameter length of the siphon and this elevation, we can start with the application of Bernoulli's equation between A and B. So which equation to be applied first? That for in order to apply the Bernoulli's equation between A and B, we must know the diameter and length of the siphon along with this elevation. Then we can start with this, and all three information we have. If it is not there, then we cannot apply Bernoulli's equation first. Then we check which information is given across A and S. So that way we can check which equation to be used from the given information. Now in this case, this elevation is given, diameter is given, length is given, so we can apply Bernoulli's equation between A and B. So first of all, we have to calculate discharge, applying Bernoulli's equation between A and B. If we put the values, this pressure here is zero. That is PA by gamma plus Bernoulli's equation means a modified Bernoulli's equation. Obviously, the elevation is given, that means the losses are there. So as far as the siphon cases, we have to use the modified equations. So PA by gamma plus ZA plus VA square by YG, that is equal to PB by gamma plus ZB plus VB square by YG plus HF. So here pressure is zero, ZA is 15 meter, V velocity is zero at this location. Then pressure is zero here, ZB is zero because with reference to ZB we have ZB is zero. Velocity is also zero plus HF. So obviously HF is equal to FLV square. HF is equal to 15. We can directly write the because whenever in the flow through pipe, one thing you remember, if the difference in level of reservoir is always HF, if neglecting minor losses. If we neglect the minor losses, difference in level of two reservoirs is always HF. It's not necessary to apply the Bernoulli's equation. So you can start with this equation. So once we get HF, then HF is equal to FLV square by twice JD. So in this equation, F is given, length is given, diameter is given. So HF is already obtained. We can calculate velocity. Once we get velocity, we can calculate discharge Q is equal to area into velocity. So discharge comes around 0.0848 meter cube per second in this case. Now the second case, that is first case, we have to calculate discharge. So that we have written. Second, we have to calculate the pressure at this particular point. Now for that, we apply the Bernoulli's equation between A and S. So applying Bernoulli's equation between A and S, we have so Bernoulli's equation at this point plus Bernoulli's equation at this point plus HF. So again, all these parameters. Now here we have to consider while considering the pressures, because most of the student make mistakes here while considering the pressures. So we have to be careful. If we are considering the gauge pressure here, if we are taking gauge pressure here, the whatever this pressure is has to be a gauge, because pressure here is most of the time negative. Not most of the time, almost always negative. PS. So most of the numerical these PS values are given, and there sometimes it is given in absolute, sometimes it is given in gauge, that is minus value is given. So if the gauge value is given, we have to consider this pressure as zero. And this pressure is essentially negative. If the absolute pressure is given, we have to consider this pressure as a absolute pressure, that is in generally at atmosphere we consider that it's 10.3 meter of water. If it is not given, if it is given, then you can whatever the given data of atmospheric pressure that you can consider. So similarly, in this case, all the terms on the left hand sides are zero because we are applying Bernoulli's equation between A and S. So here we are considering the gauge pressure because we are considering atmospheric pressure, because all the gauges shows zero reading at atmospheric. So when we consider zero, that means the pressure is atmospheric. Then here pressure is atmospheric. So this is zero. ZA, because we are measuring S with respect to A, so ZA is zero, velocity is zero. So left hand side is zero. PS by gamma that we have to determine. The ZS is 3 meter in our case, V square by twice G plus, because velocity we already obtained, and plus HF, that is not this HF, because this is HF for the entire pipe, that is AB. But this HF is only AS, that is HF for this length. So we can say AS. So here we can write the formula, that is FLS V square by twice GD. Here we have to consider the head loss for this portion of the pipe, that is inlet length. So length of that portion is considered, velocity is given. F we can consider same because the same pipeline is there. Diameter is again same. So only unknown in this equation is PS. So in case of siphon, this value, if this is zero, this value has to be negative. That is a gauge pressure. So it is obtained to be minus 7.83 meter of water. So if we can convert it into absolute as well. So now we can see here the question may arises whether the flow is possible or not. This is the numerical which is actually practically this is illogical, or we can say a wrong numerical as per the values are concerned, because practically this pressure should not be above minus 7.6. That because it if it increase above that, that means the absolute pressure falls below 2.7. That means there is a possibility of the flow obstruction. Maybe partially flow is obstructed, not fully, but the dissolved gases. So practically this is not recommended. If this kind of pressures are there, then we have to reduce this height so that the pressure here it falls below minus 7.6 meter of water. Then it is possible actually, because 10 minus that is again uh, less than 2.7 meter of water. So which is not recommended. Which is not recommended. Actually. So that's why this way you can practically you can think about it. So this is the way we can solve the numericals. So there are many cases, but every time you have to apply the Bernoulli's equation only twice. In most of the cases, we start with the Bernoulli's equation applying A and B. If not possible, you can choose this one. Almost relevant information is given. So only analysis of this siphon means we have to apply Bernoulli's equation twice. That's it. This thing you remember. You won't find difficult to solve the problems on siphon, any kind of. That's it from this session. At the end of this session, you will be able to explain the working of Siphon and its various applications. So whenever you come across some practical observations, there you come across these applications, Siphon, where it is used. So that you can easily recognize the practical, yes, this is Siphon. That is the takeaway from this particular lecture. You should be able to analyze the flow through Siphon, because flowing through Siphon that means only applying Bernoulli's equation twice, that you can analyze the siphon pipe. Siphon pipeline analysis means calculation of diameter of the siphon, length of the siphon, pressure at the summit, discharge to the siphon. These are the parameters we need to calculate generally. Or maybe in some cases, what should be the length of the inlet leg. These are the relevant parameters, geometric as well as flow parameters. That's it from this particular session. So next section, we will discuss the power transmission to the pipe. Thank you very much.